So it's an immense pleasure for me to welcome you all to this special colloquium inserted in the webinar series of the graduate program in physics of the Federal University of Pará in Amazônia, Brazil. I ask everyone to kindly leave the microphone and camera turned off, except for the moment you're going to speak. Questions will be allowed in the end, unless or otherwise requested by the speaker. The questions can be asked using the chat, both in this virtual room and in the YouTube. Today, we will have the great honor to listen to Professor Jeffrey Wineland, who was awarded with the 2012 Nobel Prize in Physics, together with Serge Haroche, for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. Professor David Wineland was born in Wisconsin, USA. He received his bachelor degree from the University of California, Berkeley, in 1965, and his PhD from Harvard University in 1970. Following a postdoctoral position at the University of Washington in 1975, he joined the Time and Frequency Division of the National Institute of Standards and Technology, then called National Bureau of Standards, where he served as leader of an experimental group working with trapped atomic ions until the end of 2017. Professor Wineland is a fellow of the American Physical Society and of the Optical Society, and was elected to the U.S. National Academy of Sciences in 1992. Presently, our special guest is Philip Knight, Distinguished Research Professor at the Department of Physics of the University of Oregon in the United States of America. Apart from the Nobel Prize in Physics, Professor Wineland research has been honored with numerous prizes and recognitions, including the Davison-Germer Prize in Atomic and Surface Physics, given by the American Physics Society in 1990, the Arthur Schawlow Prize in Laser Science, given by the American Physics Society in 2001, the National Medal of Science, given by the President of the United States in 2007, and the Michus Quantum Prize, given by the Chinese Academy of Science in 2018. Atomic clocks is what Professor Wineland will tell us about today, and I should not make you wait longer to listen to him. Professor Wineland, thank you once again very much for having accepted our invitation, and from this moment on, the audience is yours.
Okay, well, thank you for the nice introduction, and it's my pleasure to join in your seminar series here. So anyway, so I will just launch right in here. Just to summarize what I'll be talking about, I'm going to, well, first ask answer the question, why precise clocks? And the main reason for many centuries is that clocks are used in navigation, and I'll say a little bit about that. But then I'll give you the basic idea of how atomic clocks work. And more recently, people that are making clocks make clocks that tick at optical frequencies, so they're based on optical transitions in atoms. And what I'm going to do is I'm going to focus on experiments using atomic ions from my work at NIST, but of course neutral atoms are good too. So and near the end of the talk, I'll give an idea of what the status of things is and where the future might go. And throughout the talk, I'll give a little bit of personal history, and I'll conclude by saying how I got into physics at the end of the talk. So in traditional navigation, and this is still used, for example, on sailors on the ocean, is that to find the position of latitude, that is north-south direction. Basically, the idea is that an observer on the Earth can look for say the North Star, for example, and then measure the angle of the direction of his view relative to the level ground. And that uniquely determines then where the person is in terms of latitude. So that the same idea applies for longitude, but the difference is, of course, the Earth is rotating. So the idea is to still measure this angle relative of the view towards a fixed star relative to the level ground, but this angle is changing in time. So you need to know time to be able to determine longitude. Excuse me. So just to give you an idea of the errors in position due to errors in time, then I think just a simple calculation tells you that, where the error in distance is given by the radius here times the error in angle, and so that's given by the frequency times the time, basically, or the uncertainty is given by the frequency, which is once per day, times the error in time. And so just working, a simple example is for an error in time of about 1 second, and that gives an error in position and longitude of about 1/4 of a nautical mile. So there's a long history about this. Interestingly, in the early 1700s, the British Parliament, after a series of naval disasters, they sponsored a longitude act, which gave a prize of £20,000, which is a huge amount of money in those days, for if someone could make a clock that would give accuracy of about 30 nautical miles in longitude, which corresponds to an inaccuracy of time of about 120 seconds. And a famous clockmaker, John Harrison, was able to satisfy that condition. And actually, it was an interesting side story, is that although he was able to satisfy the conditions of the prize, it took him almost the rest of his life to collect from the Parliament on the 20,000 pounds. Anyway, there's several books on this, but a nice non-technical book that I liked is, if you look up that person there, Dava Sobel, you can find the book that she has. So of course, these days we're used to, the navigation is now done more precisely with satellites, for example, the Global Positioning System. And the basic idea there is that we'll assume that we have to find a position from a satellite to you on the Earth. Basically, if the clocks are synchronized, then the idea is that by some protocol, it's more complicated than this, but let's suppose we just say that the satellite will emit a pulse of radiation on every second tick, and then basically the distance is given by the time it takes for the pulse to travel from the satellite to Earth. And to give you an idea of the precisions there, the error in length, the distance to the satellite, is given by this simple expression here. And so if we can do timing to about a nanosecond, that gives a precision of about 30 centimeters. And this is basically it's close to the state of the art these days. So that's an imprecision of expressed fractionally. The 1 nanosecond over 1 day is about 1 part in 10 to the 14. And it turns out this is also then the required precision of the clock rate, or the frequency of our reference, also has to adhere to this 10 to the minus 14 precision per day. So of course, we can do 3-dimensional timing, and the idea there is that the GPS, for example, has a network of satellites, and the system is somewhat overdetermined, and the system can be, all these satellites can be checked against each other and relative to the person, an observer on the Earth. And so it gives the 3-dimensional positioning, and it also allows the clocks to be synchronized together. So what about clocks? And I think, the idea is extremely simple. It's what everybody is used to. You have some periodic event generator, and then a counter, and then from that you can generate time. And some traditional event generators or oscillators is, say, the rotation of the Earth. And up until the 20th century, pendulum clocks were actually very good, and so they provided a good reference. And and it turns out that in atoms, the oscillations of, say, an electron about the nucleus act very much like a pendulum clock. And so we tend to think in a bit fancier terms, in terms of quantum mechanics. And so rather than the classical picture, we tend to think about the oscillation of an electron density about the nucleus. But the classical picture is just fine for purposes of the clock. In any case, the idea is then that say for an electric dipole transition, the frequencies of oscillation is given by the energy difference between the two levels that comprise this electric dipole oscillation divided by Planck's constant. So one version of a clock that's been used is a maser or laser. I think people are more familiar with the idea of the laser. The maser is actually the M in maser stands for microwave. So the maser, operates on exactly the same principle. And in fact, the first devices that demonstrated the laser or maser principle was actually the maser oscillations at microwave frequency. But as I say, the principle is very much the same. So, and of course, if it's an electric dipole transition in an atom, like in a laser, this electric dipole radiates, and basically all we need to do is then pick up this radiation and then count cycles of this oscillation to generate time. So just a little personal history. Actually, I started graduate school in 1965 at Harvard. And the group that I worked in was of Professor Ramsey. By the way, can you see my pointer?
Yes, we can, Professor.
Okay, good. Yeah. So anyway, this is Professor Ramsey. That's me next to him, getting close to the boss, I guess you'd say. Anyway, this was his group in 1967, and Professor Ramsey and his close colleague Dan Klettner had recently demonstrated the hydrogen maser based on the so-called hyperfine transition in hydrogen. And that's still, that maser, hydrogen maser is still used as a timing device these days. There's better ones, but it's still a kind of a workhorse reference clock. And so anyway, this was the group in 1967. And so, Norman wanted to have accurate measurements of the hyperfine frequency of all 3 hydrogen isotopes. So my project was to build an atomic deuterium maser, and the main result of my thesis then was this was the hyperfine frequency measured for this deuterium maser. And the experiments wasn't such a big breakthrough compared to the hydrogen maser, but it taught me a lot about what was useful later in my career, and basically the idea of needing to be able to precisely control the environment to prevent frequency perturbations. I'll come back to that later. And also we could make long-lived superpositions with these masers lasting about a second. So it turns out that rather than using masers or lasers, one problem with that is that the radiation is usually in a laser and also in a maser. The radiation is captured in a cavity, and the cavity is a resonant device, so the frequency of oscillation of the maser depends on both the frequency of the cavity and the frequency of the atom, and that can be a problem because it may be difficult to tune the frequency of the cavity to be equal to the frequency of the atom. So a more common mode of operation that almost all atomic clocks work on these days is to say start the atoms in the lower state of the transition of interest, and then apply radiation at a frequency near the transition frequency for a given amount of time. And then basically what we do is we measure the probability of transition from going to the lower to the upper state. And when this transition probability is maximum, that means that the radiation source, the frequency of the radiation source, is then equal to the reference frequency of the atom, given by the energy difference divided by Planck's constant. So when this condition is met, then we basically just count cycles of the radiation from our laser source, for example, or microwave source. So why atomic clocks? And I'll try to give you a bit of an idea about that here. So I'm going to compare to a pendulum clock, but this is, the very similar considerations come into play, for example, when comparing atoms to, say, quartz crystal clocks. But anyway, I'll focus on the pendulum for this example here. So this is the simple expression for the oscillation frequency of a pendulum clock, where G is the gravitational acceleration. So one thing we can ask about is what's the sensitivity of our clocks to temperature. In the case of the pendulum clock, it's just that of course the pendulum, the length of the pendulum will depend on temperature and given by a thermal expansion coefficient. And for a very good low expansion material, usually a glass, some kind of type of glass, the coefficient of expansion is about a part in 10 to the 8th per degree C. And for most metals, it's a few hundred times larger than that. But in any case, for this example, even using a very low expansion material, the frequency uncertainty expressed fractionally is given by this simple expression here, which is about almost a part in 10 to the 8th per degree C. So the frequency would change by that amount for a given 1 degree temperature change. So what about atoms? Well, I've drawn a cartoon of atoms being contained in a box here. And actually, some of the first atomic clocks, certainly those based on microwave transitions, we actually put atoms in a glass sill that often was coated inside with a non-stick material like Teflon, so the atoms would bounce rather than stick on the walls. Anyway, the interesting thing about temperature sensitivity in that case is because the atoms are moving, we have to worry about Einstein's relativistic time dilation. And of course, the amazing things Einstein talked about us is that that basically the atoms run slower, but actually time runs slower in a frame that moves relative to us, say the observers in the lab. And so we have to account for this so-called relativistic time dilation. And I won't go through the math here, but just to give you an idea, for an atom of mass 133 mass units, say cesium-133, the frequency uncertainty versus temperature then is given by about 10 to the minus 15 per degree C. So this is about seven orders of magnitude less sensitive to temperature than, say, a pendulum clock. And a similar consideration comes in for quartz crystal clocks. They're a little better, but still there's a huge difference with atomic clocks. So the other thing to consider is the reproducibility of our clocks. Well, a pendulum clock, and for example, the distance, the length of the pendulum depends on manufacturing tolerances, and of course the pendulum clock, the frequency depends on the local value of gravity, which changes over the surface of the Earth. And of course, there's the issue of the bearing that holds the pendulum may wear, and so the length would get longer and change the change the frequency. The frequency would get slower. Well, with atoms, of course, the nice thing is that all atoms of particular kind, say cesium-133, are exactly identical, and the atoms don't wear out. I mean, as long as we can keep them in, in our container, they behave exactly the same for all time. So anyway, that the first, the first really good atomic clocks were based on cesium hyperfine transition, the transition that was similar to the hydrogen maser clock. And anyway, in around mid-60s, the definition of the internationally agreed definition of the second was based on this hyperfine transition of cesium, which was defined, the frequency was defined to be this. So the idea is you'd count so many, 9 billion and so many cycles of the oscillation of the cesium atom, and that would define the unit of time, the second. So what about, why optical atomic clocks? I said a little bit about microwave clocks, and the basic idea there, one of the advantages of having a clock based on a transition and an optical frequency is just that the tick rate can be very fast. And the simple thing there to say is that if the tick rate is very fast, then you can define any unit of time, say the second, into finer and finer intervals to get higher precision. So that's one of the reasons we want to go to high frequency, say optical transitions. And I give this example here for the mercury atomic ion, and because this, pardon me, this is where we started our experiments at NIST. And this is about, so the oscillation there, pardon me, I'm losing my voice, is about 10 to 15 cycles per second. And that's in the UV radiation zone. The other thing is that we can find optical transitions that have a very narrow absorption range. And so the lifetime of the upper state of mercury, is about 1/10 of a second, which gives a absorption feature of about 1.5 hertz wide. So the idea there is that simply this gives a very fine handle on frequency drifts of our oscillator relative to the transition. So we want very narrow transitions is the idea. So is a new idea, and actually no, the idea is actually attributed to Maxwell. It was appeared in this text that I mentioned here. Anyway, here's the passage from the paper. They certainly had the idea of of atomic clocks being, because the atoms are all exactly alike, that would provide a good reference standard. They were thinking of the optical, the light from sodium particles. Actually, pardon me, one thing interesting about this statement is they also say it's known to be absolutely independent of its position in the universe. Well, they couldn't be excused for this because they didn't know about Einstein, but I'll come back to this later. It does depend on the position in the universe, so I'll come back to that. So how do we store our atomic ions? And the idea is credited to Hans Demolt and Wolfgang Paul, and they invented the idea of the ion traps. I won't go into any detail here, but the basic idea, this is one version of an atomic ion trap. And basically we apply a combination of static and oscillating electric potentials to these electrodes. And it basically creates a 3D harmonic well for ions. And an analogy in 2 dimensions is just to say a marble in a bowl. So I'm going to talk about the experiments that we did in Boulder, Colorado, starting in this case around 1982. And this was my long-term colleague, Jim Berquist, who led this experiment, and I worked with him on the clock. And he was kind of the laser expert, is why he jumped into this project. But anyway, so I show the atomic notation here, but we can again, just label the two levels by 1 and 2. And so anyway, we apply radiation to this, in this case, a single mercury ion. The reason we choose a single ion is that if we have 2 or more ions in the trap, the electric fields from one ion on other ions can perturb the frequency. So the ideal case, in some sense, is to have a single ion. Of course, the signal is not as strong as if we only have one ion, but that's the reason we choose one ion, just to get very high accuracy. So the transition frequency there is 282 nanometers. Again, it's in the ultraviolet, this frequency here. So how do we detect these transitions? And the idea is that this is our clock transition, and there's another transition we can utilize in mercury. And actually, for all the ions we work with, we have a property like this that basically we can find another transition. The upper level of the clock transition has a lifetime of about 1/10 of a second. In this case, this P level has a lifetime of just a couple of nanoseconds. So the basic idea here is that we can, if we have a laser tuned to this transition, we can scatter light at get a very strong scattering, basically on the order of 100 million photons per second. And if we just capture a very small number, we can sense that the ion was in this state. So the idea then for detection is, let's suppose we first put the atom in the ground state, and then we try to drive this transition. If the frequency of the radiation here is tuned away from resonance, the atom remains in this level. And then when we turn on this laser, we scattered light. On the other hand, when the atom, if the clock radiation is tuned to resonance, then the atom is promoted the upper level. And then when we turn on this laser here, we don't see any scattering. So we can get a very good discrimination that way. Just shows some data here. This was the number of counts accumulated in 1 millisecond, and it shows the case where when the atom is in the ground state, we see fluorescence, and when the atom is in the excited state, the upper level of the clock transition, we see a little. This is just background scattered light, but the idea is we can set a discriminator halfway in between, and basically the nice thing is we can detect with essentially 100% efficiency whether the atom is which clock level the atom is in. So excuse me. Well, we can, in some sense, we can see an atom too. So unfortunately, this radiation for the mercury ion is in the ultraviolet, so our eye is not sensitive to that. But what we can use a simple video camera to make a picture, and this shows a picture of the central part of the trap electrodes, and you can see an outline. There's some scattered light on the electrodes, but the image in the center there is actually the fluorescence from a single mercury ion. Just one little side note is that just the size of the image we see there is limited by in part by the quality of the optics. And in fact, we can show by other means that actually the wave packet that describes the size of the atoms is about 500 times smaller than the image you see in that picture. Well, the other nice thing about this transition we use for detection is that we can also use it to cool the atoms and therefore suppress this relativistic time dilation. And if people are interested at the end, the idea is pretty simple. At least one form of laser cooling, we call it, is that the idea here is that suppose we tune this laser for detection, we tune it slightly lower in frequency than the resonance frequency of the transition. So the idea there is if the atom is moving, if this is the laser and the atom's moving against the laser beam, the first order Doppler shift then shifts the frequency of the laser up so that the atom will scatter a lot of light. If the atom is moving the other way, then the radiation this frequency is shifted even farther, farther away due to the first order Doppler effect, and so it doesn't scatter very much light because of this asymmetry. When we scatter light with the atom coming towards the laser beam, then the atom will recoil and it will tend to slow the atom down. And so this is basically radiation pressure that we're talking about, but it depends on the direction of the atom. And so by in the trap we only need to have the laser go along the have a component along 3 axes, but we could also use 6 laser beams, for example. Anyway, with this so-called radiation pressure laser cooling, it's also called Doppler cooling. For our mercury experiments, at least the first mercury experiments, the trap was at room temperature, but this radiation pressure cooling would allow us to suppress the temperature of the ions from about room temperature down to about 1 millikelvin, about 6 orders of magnitude. So that was very important to suppress the time dilation shift. So this was a picture not long after these first laser cooling experiments. Actually, I did these experiments with my colleague, Bob Drollinger, and not long after that, we teamed up with Jim Berkowitz, who I mentioned earlier, and also Wayne Atano, who had joined the group just shortly before this picture was taken. And so this was the setup during our first experiments where we started to work on mercury ions. So anyway, I'm not going to go through all the steps we went through to gradually improve the mercury ion clock. And the work started in 1981, and it reached a nice point in 2006. Just a couple of features of the clock. First of all, the fact that we're trapping our atomic ions, basically the average velocity goes to 0, which means that any Doppler shift also averages to any first order Doppler effect averages to 0. And I've mentioned the laser cooling that gives rid of the time dilation, which is kind of a second order Doppler shift. And in later experiments, we actually went to we made the trap operate at a liquid helium temperature, and that was nice because basically all the gas except for helium inside the vacuum system was just condensed on the wall, so we could drastically reduce collision shifts. Also, another shift we have to worry about is the black body radiation, the shift of the transition due to black body radiation in the room. And the thermal radiation, the black body radiation goes as temperature to the 4th power. So by going from room temperature down to 4 Kelvin, we could significantly shift reduce the black body shift. So anyway, the nice thing that for this project led by Jim Berkowitz was that basically after these many years, the mercury ion clock was the first clock that had a systematic uncertainty, which was at 2006. It was measured with this precision, or uncertainty of this precision, and it was the first clock that actually was able to outdo cesium. And the message here is that this work is still being developed on these optical clocks, but I think most people now feel that the optical clocks are the way to go in the future. But the definition of the second is still based on cesium, but maybe that'll change in the next few years. So let me come back to some other frequency shifts that we have to think about. Some of the more common ones are simply that the ambient electric and magnetic fields that the atom, in our case the ion, experiences, it shifts the frequency of the atom and of the atomic transition. And the way we can compensate for that is we measure other transitions in say in the mercury ion that have much stronger dependence on electric and magnetic fields. And that way we can calibrate the fields and then use them to correct for the small shifts of the clock transition. And I mentioned thermal radiation, the so-called black body radiation, another form of electric field perturbation. So there's the interesting effects. I've already talked about the time dilation effect due to atomic motion from Einstein. Now there's a second effect that Einstein told us about, and in his general theory of relativity. He also told us that that clocks, there's a shift due to a gravitational potential. So clocks basically run slower in a gravitational potential than they do in say, the empty universe. And just to give you an idea of the shift from at the surface of the Earth, the shift is about a part in 10 to the 8th. And so it's a big effect compared to the precisions we have now, which are around, well, below a part in 10 to the 17. So we need to worry about that. And in fact, when we compare clocks, we have to worry about you know, the relative heights of the clocks to give an idea of the you know, to be able to compensate or compensate for this so-called gravitational potential redshift. It's called the redshift. Basically, that comes from astronomers who, when they look at distant stars, they'll see a lowering in frequencies, so you know, a shift towards the red part of the spectrum. But anyway, the idea is that in a gravitational potential, the clocks will run slower. So this is the expression. I'm not going to go through the numbers here, but actually it turns out to, at least on a human scale, it's a small effect. And to give you an idea of how small it is, a little story is, so suppose you and your twin sibling were separated at birth, and suppose you live at sea level and your twin lives in Boulder, Colorado, about 1.5 kilometers above sea level. It turns out after 80 years, your twin will only be a millisecond older than you. So it's a very small effect on the human scale, but the clock, our atomic clocks now are so accurate that we have to compensate for this effect. So just as a fun demonstration of this, we did some experiments, just kind of on a human scale, checking these effects of both the time dilation shift due to motion and also the time dilation due to gravitational potential. For these more recent experiments, we switched to mercury, to aluminum ion versus mercury. And one of there was a few technical reasons. One of the nice things about this aluminum transition, it's also, the clock transition is in the ultraviolet. But the other upper state lifetime is about 20 seconds, which is 200 times longer than the mercury transition. So we get an even finer resolution on the spectrum to be able to synchronize our laser sources to. Anyway, in this demonstration, you can see this is our aluminum ion clock. A little hard to tell it's a clock. That you can see, make out a little bit. This tube here houses the ion trap, and what you see around it are a lot of optics, and in the background there's some lasers that are driving these transitions in the ion. So, but anyway, just for fun, what we did is we did two things. One is we could, if we wiggled our atoms, even at the speed you could, ride a bicycle, we could easily see the time dilation shift due to motion. But we also, in this experiment here, I'm going to show you a picture that we had. So this was one of our aluminum clocks. We had another one in an adjacent room, and it was at the same height off the floor. So when we measured the frequency ratio, it was equal with a precision of about a little less than apart in 10 to the 17, the clocks ran at the same rate. So in this sequence of pictures here, you'll see this, one of the people working on the experiment, James Chow, you can see he's put some jacks under the table of our clock number 1, and he raised it up about 30 centimeters. And we could actually see the change in frequency due to this gravitational potential redshift, which is this number shown down below here. It's about 40 parts in 10 to the 18th, the frequency changed. So just to give you an idea, that the way things are nowadays is that there's a number of labs around the world making atomic clocks based on optical transitions, and I think everybody agrees now that the optical transitions are the way to go. We still have cesium as defined as the reference for the second, but that likely may change in the next few years. But in any case, I list one reference here. It's not the most up-to-date reference, but it's a nice review of all the different kinds of optical clocks that are being used. And so the numbers maybe aren't up to date, but it gives them a nice overview of the field. So what about the future? And we still think about navigation. So with our modern clocks, we can navigate down at sort of the 1 centimeter scale. And one reason that's interesting is that, for example, as a precursor to earthquakes, usually there's strain that builds up. So say 2 locations separated by about 1 kilometer, the strain basically means that the height of these relative locations may change relative to each other. So the one application that people think about is if we can measure down to this level of precision, we might be able to measure these strains, which would be a precursor, indicator of an earthquake, and so that's hopefully that might come to pass. And of course, but there's many other things in fundamental science with our different clocks. For example, mercury versus other atoms or ions used in clocks. Their frequencies depend in have different contributions from the fundamental forces: strong, electromagnetic, weak, and so on. And since they depend in different fractions based on these fundamental forces, if the fundamental constants, the fundamental forces of strengths are changing relative to each other in time, we could possibly detect that. And at NIST we did a couple of experiments, and other labs are doing similar things to check for this idea whether the force is really constant in time. There's people are thinking of how precise clocks may also be used in gravitational wave detection. It's basically due to the frequency changing due to the motion of relative locations due to gravity waves. And there are also people come up with models that might explain dark matter, so we can look for frequency shifts that might be related to that. And of course, kind of a sport with physicists is, can we find places where Einstein's is wrong? And so far, he continues to overcome all challenges. But of course, it's interesting to see if we can find deviations. And so as the accuracy of the clocks increases, we're interested in testing, seeing whether we can find deviations from Einstein's general theory of relativity. So anyway, I'm going to conclude here, but of course, I certainly didn't know to do all this work myself. You saw the group of 4 of us in the late 70s. By the end of 2018, the group had grown to 25 or 30 people. And of course, it's all the young people, the students and the postdocs and guest workers that are doing the bulk of the work. So it's really been a big group effort, these projects at NIST. And we do have outside funding besides funding from NIST. But I also want to say that at NIST, we had a very good situation that our laboratory director, Catherine Gebbe, and now Carl Williams, I mean, they were extremely supportive of it. And Catherine Gebbe was famous for her slogan that she said her philosophy was basically, find good people and give them support and let them go. So basically, we could, we couldn't do crazy stuff, but basically, we as a group we were able to determine, what we thought was most important to work on. So we didn't have any scientific input really from our leaders. They were just very supportive. So just to say, I think maybe it's interesting for the students to say a little bit about my background. So I was, my parents grew up during the Great Depression in the U.S., basically 10 years from 1930 to the outbreak of World War II, and they were lucky that during this time they both had good jobs and they had all, and so but there was because they realized the importance of getting a college education. So basically the one thing that was ingrained in me as a young kid was to, that I needed to keep my grades up in school to make sure I could get into a good college. But my father also encouraged, with mathematics, with simple games, with math. And so anyway, they were both very supportive. And so other than the fact that they wanted me to keep my grades up in school so I could get into a good college, there was a lot of freedom to explore. So when I was younger, I was interested in model airplanes. And so I was, I did that for a long time when I was a boy. And then when I got when I got into high school age, then I got interested, my friends and I were interested in cars. And so I bought my first car when I was 14 years old, and I couldn't drive it yet because the driver's license, you had to be 16, but my father brought it home, and basically I spent the next year and a half, I tore the car all down and fixed things and built it back up. So I was always interested in cars, and my friends and I were also interested in cars and motorcycles. And so actually this is a picture when I was a little bit older, when I was in high school, and this is a group of my car friends working on modifying this 1936 Ford. And you might say, well, this is kind of a waste of time, but no, I certainly learned a lot about mechanics and working on the cars. And the other thing to say is that this teamwork was working with my friends was really like working in a experimental physics lab. I mean, all the experiments that I've described to you earlier in the talk here, I mean, we were always working in a group together. So not just one person on one experiment. It was always a group of people. So this experience of working on cars was very much like how it is to work in an experimental physics lab. I just a little bit more about my background. So after high school, I went to the University of California. In my first 2 years, I went to the Davis campus, and it was close to where I grew up. And so, but it had been and continues to be a top agricultural school, and the big time science was down in Berkeley. So I actually, in my junior year, I transferred down to the Berkeley campus near San Francisco, and in the University of California system, the transfer process was kind of trivial. All you needed to do was fill out a form, and so I transferred to Berkeley and finished my undergraduate education there. And then I went to Harvard for graduate school, and then I went to did a postdoctoral appointment at the University of Washington. It was actually with Hans Damelt, who I mentioned as being one of the inventors of ion traps. So anyway, that's it. Thanks for listening, and of course, good luck to all the students listening in their careers. So thanks very much.
So we thank you, Professor David Wineland. And before we proceed, I would just like to ask everybody to turn on their cameras for a huge round of applause in retribution to this wonderful question. Okay, so Professor, just check. Okay, so Professor, before we proceed to the questions, while people we already have some questions, but while people get ready for another questions, let me give you a panorama of the audience that you had here in your webinar today. So we have around 100 people, if we count together the people that is attending from this virtual room and the people that is attending in our streaming at the YouTube. So, well, we are mainly Brazilians, right? Most of us. So, but there's people from all the 5 different Brazilian regions. So, north, northeast, center, west, southeast, and south. States like the Pará state, where I'm speaking from, our university is, but also from the northeast, like Bahia, Ceará, Pernambuco, Goiás, in the center of the country. That is a huge country, as you know. From the southeast, people from Minas Gerais, Rio de Janeiro, São Paulo, and also people from the extreme south of Brazil, like Rio Grande do Sul, and also from Santa Catarina. So a lot of people from different universities in Brazil, but many people, many students, undergrad, graduate students, postdocs, teachers, and professors from our university, but also people from other universities scattered all around Brazil. And not only people from Brazil, as I said in the beginning, we have people attending from Spain, and we also have the honor to have Professor Barry Barish attending in the audience. So let me move to the questions. So the first question that has been registered, or the first person that has registered to make a question, is Mauricio Calvão from University of Rio de Janeiro. Mauricio, would like to turn on your microphone and make the question yourself?
Yes, thank you, Crispino. I would like, first of all, to thank Professor Wineland for the very nice and inspirational talk with the personal final touches. I have some questions. My area of expertise is general relativity, and you have already mentioned some applications which atomic clocks might have upon this area, but I would like to ask you some very specific question related to what is it you mentioned in one of your first slides, that an atomic clock takes advantage of a periodic event, and it then uses a counter to turn this into an integer number, let us say it like that. So
Right.
What is it how is it you count in that analogy of electric dipole oscillations of a quantum system of the atom? How is it you measure the number of cycles? I imagine that's what you are counting, right? Or
That's
not?
right. Yeah. So as I said, the common mode that we use is, rather than a maser or laser counting the radiation that's emitted, we probe with a laser oscillator, for example, and then we count cycles of the radiation from that laser oscillator, and that's at microwave frequencies, modern electronics is good enough that you can actually count cycles directly. And I think certainly some people in the audience know that you can't directly count the oscillations of a laser oscillator, but there's some special lasers called frequency combs, where basically you can down convert the optical oscillations down into a microwave frequency and then count those. But just to give a general answer to your question, I mean, basically we are just counting cycles of the oscillations of the radiation, so to generate time.
Okay, thank you. And another question, if I may, Crispino, and you allow me another question. It's not exactly, I guess, related to time measurements, but to polarization of light as well. What could you tell us something about the prospects, the potential of measuring accurately, precisely polarization for gravitational theories?
Well, see, I think that, yeah, I don't, maybe I'm not sure what you're referring to there. The idea of using
the electromagnetic polarization.
Yeah. Well, certainly, certainly we have to worry about the polarization, but that's not a critical component, I would say. So we just, for example, for our electric dipole transitions, we want linear polarized light typically, but we don't have to be so precise about measuring polarization for that. We just, we want it to be as good as we can get, but it's not a critical. The degree of polarization is not, a critical parameter.
Okay.
And for gravitational radiation, there the idea is it's the same idea as the current gravity wave detectors like LIGO in the U.S. And there we're looking at. We have two clocks that would be separated by some distance, and we look for, the distance changes between the two clocks via, by connecting them with radiation and looking at shifts of the, oscillations in the shift of the frequency that connects them. So, so the idea there, though, is it's just, the clocks would be test masses like the mirrors in a gravity wave.
Yeah. Okay, thank you. Thanks again.
Okay, thank you, Mauricio, for your questions. Thank you, Professor Wineland, for your answers. So the next question comes from Satish Kumar, VH from Unirio. Satish, do you want to turn on your microphone and make the question yourself?
Yes, Luis, thank you so much. Thank you, Dr. Wineland, for the nice talk. And looks like you had a good time as a kid. Do you still have your 1932 Chevrolet?
No, I got rid of that quite a while ago. But no, I mean, I wish I had it now, but I sold it after I graduated from college. So, but yeah, no, it was good training. I mean, I learned a lot about mechanics and machining and things like that. So it was valuable in my later career as a physicist.
Especially experimental, right? So my first question is there any theoretical limit on the precision you can achieve in atomic clocks because of the thermal noise and the quantum limit?
Yeah, there's certainly, well, I mean, you mentioned noise. I mean, that certainly, we have to average, to get very high precision, we average for a long time to get rid of the noise and certainly we have to, there's sort of systematic noise. I mean, maybe we have a noisy oscillator or something like that. We have to try to get rid of that. But there's the fundamental noise in the system is, for example, when I told you how we measure a transition in the atoms, if it remains in the ground state, our second laser scatters light. If it goes to the excited state, we see scattering. But the thing is, there's statistical fluctuations on whether, even in the ideal case, there's statistical fluctuations on whether the atom makes the transition or not. And it's these fundamental quantum limitations that give the fundamental limit on noise. So there's that noise process, but to maybe more fully answer your question, that just means we have to average longer, and when we measure the frequency of the radiation that's driving the clock. But to answer your question, there's really, as far as we know, there's no fundamental limit on precision. We have to, control the so-called systematic effects, we say, the things like, the motion of the atoms, which gives rise to time dilation shift. That we just have to control those better and better. But in principle, there's no limit on how well we can do there. So there's no limit in principle, on the fundamental precision we can achieve.
So that's good to know. So in that case, could you please tell us something about the fundamental science that we can do with, because we can get to arbitrary precisions, right? So we can eventually be able to distinguish standard theories from the other ones.
Yeah, I mentioned, I think towards the end, I mentioned just briefly about that. And I'm not an expert on many of the things people have come up with, but a number of theorists have come up with ways, for example, how dark matter, can shift the frequency of clocks. They have certain models for how dark matter could shift the frequency, and so I'm not an expert in that myself, but we certainly pay attention to what people are saying, and so we can. The typical thing is we can, so far nobody's discovered, with a clock. People doing clocks have not discovered any, violation of things beyond what we already know. But the hope is maybe we'll get to the point where we're going to see some deviations from the physics that we know, and that may give us a handle on things like dark matter and say, changing. The fundamental constants changing in time, for example. So.
Fantastic, thank you.
Okay, thank you very much, Tish, for your questions. Thank you, Professor Wineland, for your answers. So we have other questions here in Portuguese that I'll try to translate and maybe tell you, because since they've written in Portuguese, I presume that they are not able to ask them in English, so I will try to translate the idea as best as I can.
Sure,
so
sure.
The first question comes from Haroldo de Almeida Guerreiro. So I think the best way to do this question is, could you talk a bit about the size of the atomic clocks?
Yeah, okay, so this, the picture I showed for these earlier experiments on Mercury, what we call the trap, is sort of had millimeter dimensions, and so the typical size of the trap is actually sort of millimeter scale, but what really takes up all the room are the lasers themselves. So there's a lot of. I showed you in one of the pictures. I showed you the optical table that had all the. Had the vacuum system for the trap and so on, but and then the rest was lasers. Now actually, there's some of the work at NIST I wasn't really directly involved with, but the size of the clocks, they weren't as high performing, but they got down to basically where a complete atomic clock, including the lasers, was in a box that was sort of the size of a cigarette pack, so they could get down to scales where the entire atomic clock was on that scale. For us in the lab trying to just establish records on precision, we're not so worried about that that problem. But certainly people are now making optical atomic clocks that are portable. They may not fit in size of the size of a cigarette pack, but they're portable. They can be carried around in a car, for example. So.
Okay, thank you, Haroldo, for your question. Thank you, Professor Wineland, for your answer. So the next question comes from Edinardo Rodrigues. So he wants to know a little bit about the influence of the electromagnetic radiation in clocks, in this atomic clocks, and in time dilation specifically. So how could you say something about?
Well, maybe I'm not, don't quite understand the question.
Yeah, I mean, it's, as I said, so so under the influence, so I did not understand the question as well, but maybe you could talk about how, I mean, to the isolation of the system, I mean, to keep the system away from, because if there's some electromagnetic, let's say, is it necessary to shield the clock to avoid some noise or interference? I don't know if that's the question he's making, but I'm trying to.
Yeah, well, I mean, certainly we do. I mentioned the problem, just briefly, the problem of, ambient electric and magnetic fields. So we have to, we typically shield the trap structure where the ions are from magnetic fields, and of course, just the container, the vacuum container, is usually enough to shield against stray electric fields. Now, actually, some of the things we do have to worry about are a little more subtle. But for example, one of the noise effects we have is that the surfaces of the trap electrodes, it's an effect we don't understand, but we can see electric field noise on the surface of the trap, and the reason that's important is because it can heat the ions, and counteract the laser cooling we're doing, and we don't understand. Actually, it's a project we've been working on for more than 15 years, and other labs too. We don't really understand the fundamental sources, and it's due to stuff on the surface. We're pretty sure of that, but exactly what the effect is. So we have to worry about things like that, and that's a continuing problem that we're addressing. And one thing that helps is to go to very low temperature. Whatever the fluctuations that give rise to this noise, we can freeze it out, and so that's helped by just going to low temperature. But we don't understand the fundamental cause.
Okay. Thank you, Edinardo, for your question. Thank you, Professor, for your answer. And the next question comes from one person that is attending from the YouTube, is Giovanni Daniele from the state of São Paulo. So he congratulates you for the excellent presentation. And his question is concerned with different elements. So the cesium clock, different clock, I mean, the possibility of clocks with different elements. So could you?
Yeah. So I mean, yeah, there's a number of different ions that are interesting, and I didn't really mention the experiments on neutral atoms. There's a number of neutral atoms that are of interest, and basically the conditions are you'd like to find a transition that's not affected much by ambient electric and magnetic fields. So that's part of the choice. And the other one is just simply that, for optical transition, you'd like to find a transition where the laser is not too difficult to make, that sort of thing. So it's some of these very practical considerations that come into play. So one way to answer the question is there's no obvious choice, for an optical clock transition. In fact, that's one of the problems that, if the definition of the second is changed from cesium to some optical transition, one of the issues is that there's no clear winner on what's the best optical transition to use. So I think that'll be, a problem. These committees, the international committees that might make that decision, they have a tough job because there's no obvious choice on the best atom or ion to make an optical atomic clock. And so the worry is if they choose a definition based on a particular atom or ion optical transition, it could very well be in 5 years later, it'll be a much better atom or ion to choose. So it's a tough problem. Yeah.
Okay, so thank you, Giovanni, for your question. Thank you, Professor Wineland, for your answer. So the next question comes from Igor Moll, that is a master's student at the Federal University of Rio de Janeiro. He's in the room with us. Igor, want to make the question yourself?
Yes, I want to make the question. That's the kind of question that I should not be asking, since I am a master student, so I should better shut up and calculate. But anyway, now let's go. Well, Roger Penrose has written a lot about the coherence and gravitational fields, how strong gravitational fields can induce decoherence. But Roger Penrose has always been a very creative person. What surprised me is that in the event commemorating the 50 years of the Standard Model, both Gerhard Stoft and Steven Weinberg talked about foundations of quantum mechanics. Since I do not believe Gerhard is going into the right direction, let me only comment on Steven Weinberg. He is arguing that corrections to ordinary quantum mechanics, as described by the Lindblad equation, might be detected by exploring the great precision of atomic clocks. And I would like to know your comments and what you think about those ideas. I know that's very speculative. That's why I should not be asking this. I should be doing exercise and training for my examinations, but as I have already made the question, what can I do now?
I think as a experimentalist, I think we certainly haven't, me and my colleagues haven't come up with any, possible new, theoretical terms that would give rise to fluctuations. But I think, so our job has been to try to look for these speculations about, new effects in quantum mechanics or whatever that might affect the clocks, and then put them to test. So I think, we're more the, just the people in the lab trying to check these ideas out. So, yeah. Anyway, no, but we certainly try to stay plugged into what people are thinking about and seeing if our clocks can put limits on these effects that people are coming up with. So,
I see. Well, thank you for your very thoughtful answer.
Thank you, Igor, for your question. Thank you, Professor Wineland, for your answer. So the next question comes from Márcio de Miranda. I think he's in the room. He's raised the hand, and I did not pay attention to that. So, Márcio, do you want to make the question yourself?
Yeah, thanks for the nice talk, Professor. And my question is, have you thought about a different platform other than atomic gases or neutral gases or ions that could achieve such high precision and high accuracy as atomic clocks?
Well, the reason so the reason we choose neutral atoms or ions has been that we can exercise pretty good control on their properties. But when you say this, and an interesting example people are thinking about, over the last few years, is that there's an optical transition in thorium-229 that it's actually a nuclear transition, and it's at a fairly short wavelength, but still one that can be achieved. It's about 150 nanometer wavelength transition. But the reason that transition is interesting is that one way to say it is that the nuclear levels are strongly shielded by the outer about the outer electrons in an atom, or the surroundings in a solid. So one of the things people have thought about is looking at thorium atoms or ions directly to measure this nuclear transition. But people are also thinking about having, say, thorium in a solid, where still the nuclear transitions are well shielded by the surrounding environment. But that could, in principle, provide also a very, a good transition for an atomic clock. In this case, nuclear, but it's because the nuclei are so well shielded from the surroundings why that's interesting. So there are several groups working on trying to see this transition in thorium that that it so far hasn't been seen, but I'm sure people will see it in the next few years. And anyway, so that's one example. But to answer your other question, I think it's just there could be other transitions, but they're usually they're usually dependent on the material the medium is in, that what the frequency is. So we want something that's fairly well defined, say a nuclear transition, or in the case of an atom, where we can confine the atom with external fields. Then we want to get rid of the perturbations from whatever's holding the atoms or the nuclei. So.
Okay.
Okay, thank you, Marcio, for your question. Thank you, Professor Wineland, for your answer. So, Professor, I think we are coming close to the end. But before that, let me ask you one or two questions. I mean, or at least ask you to talk about some things. So, could you tell us your thoughts about time being continuum or discrete? I mean, so people, so would you like to say something about that?
Well, I've heard these ideas about discrete time, but I'm just not up to speed enough to really comment on that. I mean, certainly, I would say all of us in the lab, we think of time as just as a non-scientist would think about. It's a continuous, parameter, and but I certainly haven't heard of any ideas how that those ideas might be checked with clocks. But if someone came up with an idea and we could test that, we'd certainly be interested in that. But anyway, I as I say, I just haven't done enough looking into that to give you a good answer.
Okay, thank you. And so just to finish, I mean, before, maybe as your final words, if you would like to say a little more about the main challenges for the atomic clocks for the future, and then just we come to a closure, Professor.
Yeah. Well, as I was saying earlier, as far as we know, there's no fundamental limits on how accurate we can get. How much we can reduce the perturbations to the clock. So I would say that the approach has always been we want to try to find maybe atoms or ions that are more advantageous. But so I think it's just a continual game trying to find systems that control better and better, and so that that's. We need to search and look in different places, but I think that's part of the process. All of us working on atomic clocks are faced with. We want to find a system that we can control better and better. And so, at least in that sense, it's a pretty straightforward problem we're trying to deal with.
Okay, Professor. So once again, I would like to thank you very much for this wonderful time that you have allowed us to be with you, listening to you and learning from you. And as a final retribution for that, I'll ask everybody to turn on their microphones once again for a final round of applause. Thank you very much, Professor.
Thank you.
Yes.